Electric flux is defined as the rate at which electric field lines pass through a surface. We can measure electric flux as E dot A, where E is the electric field lines as a vector and A is the area vector. This can also be written as the magnitude of E times the magnitude of A times the cosine of the angle between them. Now, let's analyze these electric field lines passing through a square surface. The area vector is always normal to the surface. In this case, we will write that the area vector faces outward, away from the electric field line direction, but it does not matter, for if we have a plane, we can define the normal in either the front or back. In this case, we will say that the area vector points anti-parallel to the electric field. The only difference that this makes is that the area vector will either be cosine of 0 degrees from the electric field or 180 degrees, making either a net positive or negative flux. So, if we want to find the actual flux for a square of side length s, we would do E times s squared times cosine of the angle between E and A, which in this case is 180 degrees. So we would get negative ES squared. Now, let's imagine we had a cube instead, and that the electric field lines pass through one face of the cube and out the other. Now, for a closed 3D object, we consider the area vector to be pointing away from the center at each face. So the area vector we defined would be correct in this case for pointing out. And the area vector on the opposite side is the opposite direction, still normal to the surface, but pointing away from the center. The other four faces do not matter, since they do not contribute a net flux. This is because their area vectors are 90 degrees or perpendicular to the electric field lines. So the dot product evaluates the cosine of 90, which is 0. The total flux now from the other side will be cosine of 0 because the area vector and the electric field lines are parallel. So you would just have ES squared. To find the net electric flux, we sum up all the contributions from the individual faces, where the four of the faces are 0. So we just have ES squared and negative ES squared, giving us 0. Which is true for the net electric flux through all closed objects with 0 enclosed charge. Let's now consider an electric field passing through a square plane at an angle theta, where the area vector is still normal to the surface. So the net electric flux would be E times A, which is S squared for side length S, times cosine of the angle between the area vector and the electric field, which is theta. So, what would happen if we increase the angle theta? As we increase theta and it approaches 90 degrees, cosine of theta approaches 0. So as we approach 90 degrees, the flux becomes 0. And as we increase it, the flux increases non-linearly because cosine is a sinusoidal function. Let's look at Gauss's law and the Gaussian surface. A Gaussian surface is just a surface that encloses a charge or charges that produce electric field lines. Electric flux we normally define as E dot A, but since a Gaussian surface can be a much more complex shape, in order to find the total electric flux at all the given angles of the area vectors with the electric field vectors, we sum up all the infinitesimal electric fluxes with the surface integral of a closed loop, hence the circle, of E dot dA. This is the generalized formula for electric flux used in Gauss's law, which also equals charge enclosed over epsilon naught. This is the fundamental concept of Gauss's law. The electric flux through a Gaussian surface is proportional to the enclosed charge. It is independent of the shape of the Gaussian surface, whose electric flux we sum up with the integral of E dot dA. But, in general, electric flux is proportional to the charge enclosed. Let's look at the example below. We see a Gaussian surface that encloses 2 positive charges, 3 negative charges, and 3 external charges around it. But we know electric flux is only proportional to the enclosed charge, so all that we care about are the charges inside the Gaussian surface. So adding the positive charges of charge Q, we just have 2Q, and for the negative, negative 3Q. So the net electric flux to the Gaussian surface is just negative Q over epsilon naught. Let's now imagine that we had an additional positive charge, so that the 2Q is now 3Q, and the net electric flux is 0. Does this mean that the net electric field is also 0? No, not necessarily, because we're just saying that 0 equals the surface integral of E dot dA. So therefore, that doesn't mean that the electric field is necessarily 0. If we consider the net electric flux from a single external charge, it goes into the Gaussian surface and out, therefore contributing a net 0 electric flux. But the electric field through one part of the Gaussian surface can still be non-zero. So external charges can make it such that the electric field is not 0 even when the flux is 0. Let's consider a Gauss's law problem with an insulating sphere of charge plus q that is uniformly distributed inside of the sphere and radius uppercase R, surrounded by a conducting spherical shell of charge negative q that is also uniformly distributed. To start, let's write Gauss's law, which is the surface integral of E dot dA is equal to the charge enclosed over epsilon naught. So let's first consider the charge enclosed. The charge enclosed here, if we draw our Gaussian surface at radius big R, we'll see that the Gaussian surface encloses the entire insulating sphere. And by enclosing the entire sphere, that means it also encloses the entire plus q charge. So the q enclosed is just q, therefore resulting in q over epsilon naught. Now, to simplify the E dot dA, since we're outside of the entire insulating sphere, let's pretend that the entire charge enclosed is centered at the very center of the insulating sphere. Therefore, the electric field lines pass through the surface parallel to the area vectors that face away from the center of the sphere. We can now rewrite the integral of E dot dA. Because the electric field lines and the area vector lines are parallel, E dot dA is equal to E times dA times cosine of 0, which results in just E times dA. And since E is not a function of A, we can pull E outside the integral and get E integral of dA, which equals E times A. Now that we have this, we can set E times A equal to the charge enclosed over epsilon naught. Since we are considering a sphere of radius big R, the area of a sphere is 4 pi r squared. So E times 4 pi r squared equals q over epsilon naught. So therefore, the electric field is equal to q over 4 pi r squared epsilon naught. That's the answer for the electric field at the very outside of the insulating sphere. Let's now consider the electric field for a Gaussian surface of radius small r is less than big R. So, writing Gauss's law, we have the integral of E dot dA equals the enclosed charge over epsilon naught. Drawing out our Gaussian surface, we can see that the volume of the Gaussian surface does not enclose the total volume of the insulator, so therefore the enclosed charge cannot be the full plus Q charge. The only time that that happens is when our Gaussian surface fully encloses the volume of the insulating sphere, since it has a continuous and uniform charge distribution. To find the enclosed charge, let's consider the volume charge density ρ, which equals the total charge over the total volume of the insulating sphere. This ratio is equal to the enclosed charge over the volume enclosed by our Gaussian surface. So to solve for the enclosed charge, we just cross multiply and get that enclosed charge equals the total charge times the volume enclosed over the total volume. Solving for this, we get that the charge enclosed equals Q times the enclosed volume 4/3 pi little r cubed, the radius of our Gaussian surface, over the total of the insulating sphere, 4/3 pi big R cubed. Canceling, we get that the enclosed charge equals Q, the total charge, times small r cubed over big R cubed. Keep in mind that this relationship with the ρ and the ratios of the charges and volumes is only true for charge distributions that are uniform. So now, using Gauss's law, we have E times A, since it's spherically symmetric, our Gaussian surface, equals Q times small r cubed over big R cubed times epsilon naught. The area of our Gaussian surface is 4 pi little r squared, equals Q r cubed over big R cubed epsilon naught. Solving for the electric field, we get Q times R over 4 pi big R cubed epsilon naught. Considering the Gaussian surface at radius r equals 1.5 big R, and sketching the surface, we can see that the Gaussian surface encloses still the plus Q full charge of the insulator. Since there's no charge between the conductor and insulator, the charge enclosed is still positive Q, and the flux is Q over epsilon naught. So rewriting Gauss's law, E times 4 pi little r squared equals Q over epsilon naught. So the electric field is just Q over 4 pi r squared epsilon naught. Now you may be wondering, isn't this equal to the electric field for a Gaussian surface at radius big R? Yes, because the charge enclosed is still the same. The only difference is the R is a different distance, so the electric field would be weaker, but the formula is the same. Let's consider the electric field at a radius r is equal to 2 big R. This means that the Gaussian surface lies within the conductor, meaning that the electric field is zero. Insulators do not allow for the free movement of electrons or charge, so the charge is evenly distributed throughout the insulating sphere. Meanwhile, for a conductor, which allows the free movement of charges, in order to minimize the repulsion between the individual charges, they will evenly distribute themselves around the outer surface of the conductor. Now, considering the Gaussian surface within the conductor, knowing that the electric field is zero, the only way that that could happen is if the enclosed charge is zero. But we see that there's positive charges within the insulator. So how could we cancel that for it to be zero if the only charge contained within the Gaussian surface is positive? That means that negative charges must collect somewhere inside of our Gaussian surface to cancel that, which in this case would be the inner surface of the conductor. So now, if we have a positive plus Q cancelled by a negative Q, the enclosed charge is zero, therefore allowing the electric field to be zero. But by conservation of charge, we can't just create extra charge. So the positive charge must collect on the outer surface of the conductor in order to conserve the initial charge that we had. Writing this in terms of Gauss's law, we have the surface integral of E dot dA equals the enclosed charge, which we have negative q and plus q, so 0 over epsilon naught, therefore making the net electric flux equal to 0. But in this case, we know the electric field inside a conductor is 0, so the electric field is 0, as well as the electric flux. Now let's consider the electric field at a radius r is equal to 3 big R. So in this case, it would be easier to refer to the initial conditions that were given. The insulator has charge plus Q and the conductor has charge negative Q. So the net charge enclosed is 0. Even if we consider our updated charges, considering the conductor, we still have a net charge enclosed of 0.